When developers tried to connect a large language model to external tools or internal data silos, the underlying architecture tends to shatter under pressure. The core problem is that every API behaves differently. Integrating a model with a CRM, a database, and an email server requires writing bespoke integration code for every single endpoint. This creates a highly fragile environment. The moment a model's underlying architecture updates, the hard-coded connection logic often fails. This schematic exposes the resulting system architecture. On the left, we have deterministic APIs, operating like rigid interlocking gears. On the right, a probabilistic language model acts as a fluid, expanding network. Forcing them to interact requires a chaotic, tangled web of glue code. The Model Context Protocol, or MCP, was engineered by Anthropic to address this specific structural failure. Rather than operating as a proprietary system, MCP functions as an open-source standard that is being adopted across the industry. Scaling AI infrastructure relies on moving past individual point-to-point integrations toward a shared, standardized communication layer. To understand why the old methods fail, we have to look at the original design intent of REST and GraphQL APIs. They were built for programs written by humans. These traditional APIs are strictly deterministic. A developer writes a precise, predefined request, and the server returns the expected data. Modern language models operate differently. They are probabilistic reasoning engines. An LLM processes uncertain inputs and generates text based on probability. Before it can execute a complex action, it often needs to explore its environment, ask clarifying questions, and dynamically adjust its approach. When a probabilistic model is forced to guess the exact syntax of a deterministic API endpoint, it results in hallucinations and failed calls. A rigid, deterministic bridge cannot natively support a fluid probabilistic engine. This gap requires a dedicated translation layer. This diagram outlines the core of MCP, splitting the architecture into two distinct nodes, clients and servers. The client acts as the reasoning engine, like Claude or Gemini. The server is the isolated environment exposing resources, like a file system, SQL database, or corporate tool. Under the old method, the client blindly requested specific data endpoints, relying on the programmer to have hard-coded the exact syntax the server expected. MCP reverses this flow. Upon connection, the server actively advertises its supported capabilities and required inputs back to the client. The model is no longer pre-programmed with API endpoints. Instead, it maps its available environment dynamically. This dynamic capability mapping allows the model to understand its context through the protocol, rather than requiring developers to document every endpoint manually. By shifting from hard-coded paths to dynamic discovery, the protocol provides the mechanism an AI agent needs to route its own tasks. For this discovery process to work, both sides must share a unified communication syntax. This visualization shows the specific structured JSON schema that MCP uses to bridge the client and server nodes. It defines capabilities through strict key-value pairs. When the client needs to interact with the environment, it formats a JSON request to list available resources or call an action. The server's JSON response then packages both the limits of what is possible within its environment and the actual results of any executed actions. This single schema handles validation and execution uniformly, regardless of whether the underlying system is a SQL database or a file repository. Standardizing this JSON discovery syntax allows a single model to interrogate endless external systems without requiring manual code changes for every new tool. As shown here, the MCP schema organizes all interactions between the AI and its environment into 4 strict resource categories, known as primitives. The first primitive is tools. These are the specific executable actions the model can invoke, like triggering a search or dispatching an email. The second primitive is resources, representing read-only data and state information. A text document, database row, or image file all function as resources. The third primitive, prompts, acts as reusable behavioral templates. They dictate how the model should approach specific server-side tasks. The fourth primitive is context. This is external reasoning data the model pulls in, such as user preferences, chat history, or internal guidelines. By organizing the external world into these 4 primitives, the protocol provides the LLM with a predictable way to interact with any system. Let's track a practical architectural case study. building an autonomous agent that manages a calendar, reads meeting notes, and drafts follow-up emails. Previously, a developer had to write explicit Python scripts to handle the distinct rate limits and authentication protocols for the Google Calendar, Notion, and Gmail APIs. The system relied on complex prompts to teach the LLM how to format every single API request for those specific services. In the MCP approach, you spin up 3 compliant MCP servers: Calendar, Notes, and Email. These servers manage their own internal logic, while the central model connects to them directly through a single protocol. The LLM reads the advertised capabilities of all 3 servers simultaneously, such as list events or get summary, and then plans its own execution order. The model handles the data passing between the tools, guided by the unified JSON schema. This shift removes the need for manual glue code, allowing the model's reasoning process to handle the task mapping that once required custom integration. Adopting MCP does not require tearing down existing REST or GraphQL infrastructure. This diagram illustrates how the protocol functions as an abstraction layer. It sits between the LLM client and your foundational APIs. On the backend, the MCP server still executes standard REST or GraphQL calls to access databases. However, the language model is shielded from backend complexity, interacting only through the unified MCP schema. This layered architecture enables engineering teams to expose legacy systems to any compliant LLM without requiring a custom rewrite of the original API. MCP optimizes for the reasoning process of an agent, providing a standard interface that is distinct from the manual coding requirements of a human developer. The currently fragmented state of AI tool integration mirrors the isolated mainframes that existed before the World Wide Web. HTTP provided the shared language that allowed disparate computers to form the Internet. Similarly, these disconnected nodes now snap into a unified grid through MCP. The protocol is beginning to do for AI tool use what HTTP did for web communication. For enterprise software, implementing MCP server compliance is transitioning from a novelty to a baseline requirement. Understanding this abstraction layer enables developers to transition from writing manual integration scripts to designing the architecture of autonomous systems.
Thank you. Share and subscribe to Learn AI for more AI insights.